I want to look into more specific details about the structure of the hyperbolic figure-8 knot. You'll see there's going to be a few creative ways to look into it. We'll start with our equation of our bipart dialogarithm. The first one's under the argument of 1 over the imaginary golden ratio. Take the difference between that and dialogarithm of under the argument of the imaginary golden ratio. Just to remind everyone, I is the square root, or power of 1/2 of -1, and the imaginary golden ratio is 1/3 power of -1. So this is one of the ways we can look into the structure of the hyperbolic figure-8 knot. This is an equation that gives us the hyperbolic figure-8 knot, right? So VFE. Now, a couple things we can do. First thing is, let's look at this piece by piece. Let's take just this piece here and this piece here. They're kind of similar. They're both dialogarithms, so they're functionally exactly the same, but they're under opposite arguments. Okay, well, let's see, but what are they individually? 4 pi over gamma of 5 squared minus the Geekskin constant times I. So there we go. The first chunk, it actually splits into 2 pieces, a real piece and an imaginary piece. The imaginary piece is the Geekskin manifold. The orthogonal real piece is 4 pi over 24 squared, which I'm writing as gamma of 5 for a reason, but you can think of it just 4 pi over 24. It's equivalent. The other piece, the second piece, also splits, and its real part is exactly the same, 4 pi over 24, or gamma of 5 squared, and plus GGI times I. All right, now we can see when we take the difference, this one minus this one, all times by I, that the thing comes out to be just 2 times GGI, right? Play with it if that's not immediately obvious. We've done that before a few times, but this is a great structure to look into. Each piece of our dialogarithmic structure that's responsible for making our figure-8 knot, our minimal possible hyperbolic root to make a hyperbolically projected system, each piece there splits into a real and imaginary component. These were orthogonal expressions of the structure. So they split, but they also split in opposite form in the imaginary way. So this one's got minus GGI times I, and this one has plus GGI times I. That's one way to look a little further into the structure, but here's another way. When you have an operator that is equal to negative 1 over 3 power, that's basically saying you're taking a unit circle and you're splitting it into, here's your operator right there. But you're not just doing that one. This is 1/6 of the circle. So really you split the whole circle into 6 pieces. That's what you're really doing. And this is addressing the magnitude of the splits. So the first piece tells you how far you go in one piece, and then you know after that it's just multiples. And this one's imaginary golden ratio to the 0 or to the 6 or to the 12 or ... right? Technically, you can see at this point how the modular structure works. All of these powers, this is a power of 1 here, or add 6, or any multiple of 6 to any of these, and you would get the same position. Okay, but this structure, this number here, is dividing the unit circle into 6 pieces, right? It's a unit circle divided into 6 pieces. In the same similar way, I is talking about a unit circle divided into 4 pieces, right? So this is for imaginary golden ratio, and for I, we're talking about a unit circle that's divided like that. That's it. So there's a 4-fold symmetry under power operations, because when you square under rotations, you just double your rotation. Okay, so there's a perfect symmetry. The number of powers you go up to is just the number of multiples that you rotated. All right, so here we have a 4-fold symmetry, and here we have a 6-fold symmetry. And we think that these operators are centrally here because they're talking about how the system is a system that splits up in 4 ways one way and 6 ways another way. Okay, this is fantastic. And connects all of its pieces back together. That's a beautiful thing. It closes on itself. But still, it's splitting in 2 different ways, 6 and 4 pieces each. Okay, let's look a little further now. Let's keep track of the relationship here fundamentally in our structure between this piece and this piece, showing up both times at the beginning. Okay, so the 2 pieces here, because I need the space, so just need to keep track. We have a Gies-King constant, and we have 4 pi over, let me write it as 24 squared, just to be different, so make sure it's clear to you that that's the same thing, right? These are the 2 guys we're keeping track now. But they have a direct relationship. They are orthogonal pieces of each other. Okay, so in the structure, when you care about this, you have to care about this. Well, obviously, because you're building the double cover of it. And that double cover comes with 2 pieces that have this in it. You can either cancel them out, or you can add them together, or you can multiply them, right? Or you can divide and get 1, but whatever. That piece, this geometric structure, is inherently orthogonal to the manifold we're talking about. So it's part of it. Okay. A little more space. Let's generalize, or let's talk about the symmetries of this structure under each of the possible rotations that must be there. Let's just look. How does this go if we say, let's generalize this form here with an n in both cases. Okay, so we started out with n equal to 1 and it gave us that, but now that I've done this, I can't say it just equals that because I have to specify my n. So now we can make a chart. All right, what happens when we put in 0 here and there? Anything raised to 0 is equal to 1. 1 over 1, just 1. 1. So these things become identical, the whole thing becomes 0, because we're subtracting the difference between them, but they're identical. So that becomes 0. Okay, what happens when we put 1 in here? Now we get what we originally had, and we get the hyperbolic figure 8 knot. All right, so right now we have a pattern developing who starts at 0, and its first step is hyperbolic figure 8 knot. What's the next step going to be? Any guess?
2 VFE.
That's a great guess. It's very close too. Turns out it's 2/3 VFE. And then 0. If we put 3 in here and there at the same time for n, we get 0. And then we get negative 2/3 VFE. And after that, we get negative VFE. And then we get 0. And this 0 is the same as this 0, because the pattern after that repeats infinitely. So there's a 6 cycle built into the structure we're starting with. So we need to really take note of all of that structure. This 6 cycle tells us if we take our structure we start with and just give all of the rotations, but then you can extend it infinitely. When you do, you get this cycle of repeating numbers, which is really a 2-part, or I'll just call it a bi 3 cycle. You notice there's a 3 cycle in there with the zeros. Every third is a 0. Okay, but we've turned around upside down every time in between. So there's a reflected 3 cycle that makes our 6 cycle. So it's a 6 cycle that's of most simplicity. It's not even 6 different pieces, it's 6 reflected pieces that are the same except for sign. I'm going to do this on Wolfram Alpha real quick so that you don't have to trust me that this is true. Right now I just wanted to look and see the 6 cycle. But let's talk about the properties of the 6 cycle real quick. It's a nice step to look in, like Euler would have done this, or Euler. Right? If we take the sum of the 6 cycle, what do we get? Perfect. Because everything cancels. This plus this is 0, this plus this is 0, and zeros are 0. Yeah, so if you take all of them in the 6 cycle that repeat, you get 0. So another balance that way. The total sum is 0. If you take the non-zero sum, so take all the parts that aren't 0 and add them together, you also get 0. Okay, let's look at the product. Of course, the product is going to have to be, if you multiply them all together, if you multiply all these together, what do you get? 0, because 0 times anything is 0. But if you try to look at the non-zero product, multiply all the things that are not 0 together, this time we get.
That's interesting.
That is it. Why is this interesting? Because we believe that this structure is responsible for the simplest possible hyperbolic stage that you can make. I mean, a perpetual stage that inverts on itself, divides in pieces that fold into themselves, but the simplest possible one. And we think, therefore, that reality, or nature, is using that stage. So if we can understand the stage to higher precision, if we can understand all of its degrees of freedom, the symmetries built in, the things you can do with this structure, then we'll understand the way things are dividing to higher accuracy. Right? We'll have more of a picture. So we're following the features built in so that we can start to understand, oh, what's natural to this system? And so far we notice just the dialogic bipart structure here. If you fix the structure, you can't change the form, but you can change the power of the rotations. Okay? We're even sticking to the rotations being similar, and you can only hop to the rotations that are invented by the fact that you put 1 into the system to begin with. Okay, over and over and over. This is a built-in structure, or structural feature of the form we're interested in. Okay, one hidden new feature, a bunch of zeros there in that 6 cycle, but one non-zero product that's got a natural 36 division in it. This is interesting. Let's remind ourselves why. Which numbers are we most interested in when it comes to our system? Well, we remember when we set n equal to 1 in both cases, or get rid of it, then this is the hyperbolic figure 8 knot. And if we then get rid of the I and try to ask what's the inverted projection of the same connection, or the real part of the exact same thing if we turn it upside down, or turn it inside out, put a plus sign here instead, get rid of I, the same structure then kicks out 4 pi squared over 288. So 288 is our division structure. It's the number we're really going to care about when we're talking about a system that breaks into numbers of pieces of different sizes that fit into each other. So the natural divisors of 288 are 1, 288, 2, 144. So we've paired them to show what we mean by factors even, right? Every one of these pairs is equal to, when you multiply them together, 288. So these are all the factors, the way you can break up 288 naturally. All right, there's some ones that stand out for us. First, this way of factoring is the way that we're devoting our energy to in the poster, right? All of the ways of factoring are true. I'm not saying one's better than the other. This is the way that we've framed so far. You can frame it in any of them in the multiples. The system we're talking about should be factoring in a way that's compatible with this whole set. Beautiful thing to keep in mind. There's another ones here. 18, 32, 8. Those three are the degrees of freedom available to the Planck mass, the Planck temperature, and the Planck charge. Yeah, it's a symmetry line after this. So everything inverts. And actually, what did I do wrong? It should be 16 here, huh? Yeah. There we go. All right, so what am I pointing out? I'm pointing out that the division structure that we're starting with the 5 different Planck constants, the external system is Planck charge, Planck mass, and Planck temperature, right? These 3 degrees of freedom are part of the natural ways of dividing, or the modular whole number that's attached to those boundaries are natural divisors of 288. That's great. It's a fantastic thing. You don't have to try to make them fit. They already fit naturally. Great. So we're trying to understand that division process, which means it helps to keep in mind that the division process has many ways of talking about it, right? The system divides up naturally all of these ways. Okay. Next step. There's another cycle built in to the same structure if we modify now our argument to the other argument we know at least is in the system. That one. So now we're going to do I to the n and I to the n. All right. If you remember, when n is 1, this now kicks out 2 times the Catalan constant instead of 2 times the Giesecke constant. So the Catalan structure is in the system at the same time, right? We didn't change the structural components, we changed just the argument, right? The same arrangement and everything, but the argument that's being used went from this one to this one. Okay, the pattern we get there is just 4-part, you might guess, right? The Catalan pattern, if you go up in powers, is a 4-fold power symmetry system, right? 4-fold meaning because we're using I, it has to be 4-fold. So for 0, of course, the same thing happens, it's 0. They cancel out, right? If it's 1, we get 2 times the Catalan constant. If it's 2, we get 0 again. If it's 3, it's negative 2 times the Catalan constant. If it's 4, it's 0, and on and on. Every other time we change signs with a 2 times Catalan, and every other one is a 0. Pretty easy pattern to remember. The components here are all going to be 0, 0, 0, except this part, again, will actually have a non-zero entry. So our non-zero product here is equal to this times that, negative 2k squared. That's really pretty. Really pretty. I'm sure you've seen 2k before. In fact, 2 times the Catalan constant is also equal to 2 pi times c sub d, or the domino tiling constant. 2k is also equal to the natural log of the dimmer constant to the power of pi. Okay, so the dimmer constant and the domino tiling constant should now be on our radar. We want to know what structural information do they contain. If they're part of the system, then whatever the structure that comes with them is another clue about what structure exists in the system. So, great. This one has a relationship. It's equal to, in fact, the radius of the neutron over the radius of the electron. It's what we currently believe. It's true within the data points we have. And it makes a lot of sense that we're dividing our system, our simplest possible system, along the boundaries of the actual structural components we find in reality. This is a great thing. But also the Giesecke constant, sorry, not the Giesecke constant, Catalan constant is equal to radius of the neutron over radius of the proton. Radius of the neutron divided by radius of the electron is equal to 4 pi over 24 squared. Now, hopefully at this point, you see a direct natural connection between this number and this number. And the fact that both of them perfectly line up with the ratios of the radii of the things that construct atoms should be quite intriguing. I find it quite intriguing. Okay, this is a beautiful lineup. All right, so what I want to do now is switch the computer and look at this in Wolfram Alpha so you can see the sequence pop out. So, and then we got a little fun thing to close up with after that. Many ways you can type on Wolfram Alpha. There's many natural ways. So here's a structure I'm writing. Let me put a 1 in for the argument to begin with, minus dialogarithm of 1. After you type the equation, it'll show you what it thinks you meant, right? Fantastic. All right, well, I need to change my argument now here to be -1 to the 1/3 power in both cases. Oops. Actually, in the first case, it needed to be 1 over that. 1 over. Okay, second case. -1. All right. Now we've got the difference between two dilogarithms. The first one's argument is 1 over the cube root of -1, and the next one is the cube root of -1. Perfectly. That's what we wanted. Perfect. Now, we can't write the imaginary golden ratio yet. Hopefully, in an update in Wolfram Alpha in the future, that'll be a thing you can just type in. Right? It would make this equation look even more beautiful if this whole thing just collapsed to the symbol for that thing that's, I think, accepted out there. Anyway, but you can probably see into there. This is the equation we meant. Okay, and below it tells you what it's equal to this many digits at least. This is higher precision than we have any measurement in physics of the constants of nature, so I don't need that much precision right now to ask what I'm doing, but you could just ask all of that. And I want to know, what is this number? This is an interesting number. Well, it's equal to, well, either 2 times the Giesecke constant or the hyperbolic figure 8 knot, which appear to be exactly the same numbers out where it's highlighted and even further. Yes, okay. So, great. If you don't know what those things are, you can then click on them, right? And it takes you to a page that defines very interesting properties, and we will be getting back to that soon. Oops, I need to go this way. Okay. So now what I want to do is let's take our same arrangement, and we're just going to multiply the rotation by another power every time. So right now it's 1/3, so we want now to go 2/3, and then 3/3, and 4/3, and 5/3. But every time we change this first one, say go to 2/3 there, we have to also go 2/3 here. So we keep the same exact structure, we're just changing the power of our rotations, and now we get a new answer. Right? It didn't even start with the 2, it's a totally different answer. So let's ask what is it? Let's see, I didn't reduce it. With all those digits, it still tells me it's 4/3 the Giesecke constant, or 2/3 the hyperbolic figure 8 knot. All right, so this is the investigation process that's made incredibly easy and fast by this engine. So let's go up another power. 3/3. This is cubing it now. It's the same thing as bringing it into the power. Uh-oh.
Oh, we're making it 1.
Now it's 0. Yes.
Oh, yeah.
0 now. Interesting. Okay. So now that we've hit 0, is it just going to stay at 0, or what happens if we keep going up? 4. Huh. That looks suspiciously like the other number we just saw, I think. Let's check.
Minus.
It's equal to, yeah, except for the minus. Yep, exactly. Okay. Now we have a pattern emerging. It's starting to be familiar. We can kind of guess what's going to happen here. 5/3. Ooh, we like this number. It's very familiar. It's negative hyperbolic figure 8 knot. Great. All right, and the pattern now we can expect to repeat. So 6, 6, 0. And then we're off in the races, and it continues and continues and continues. All right, same thing we showed up here, hopefully. If we change the same thing, let's put in I instead of So to put in I means I have to change this to 1/2 power. Okay, good. So we switched our argument here to I because we changed the power to 1/2 instead of 1/3 for the rotation. So it's 1/2 of a flip now instead of 1/3 of a flip that we're talking about. And when we do that, we get 2 times the Catalan constant. Now, no, they're using capital C for Catalan constant, and Catalan constant, I'm using capital K because I have too many C's as it is, but it's also sometimes capital G. It's got amazing, amazing properties. We're going to get into some of them as we go down. I'm just scrolling real quick so you can see. Look how much is known about the Catalan structure. This is all stuff available to understand about the structure of our simplest possible hyperbolic stage. Okay, now remember the Catalan structure is to be understood part of the same structure under different rotation. Okay, so it's under different rotation and it splits with a different number of pieces. So there's 2 components that are really important. All right, so the first thing I just want to point out here is we're just looking at, let's make it bigger, a little less big, there we go. Different algebraic ways to write the Giesking constant. Okay, so these are all true statements, so they all give you insight about ways to think about the structure of the Giesking constant. And I want you to notice real quick that there's 1/36 here. Okay, if we write it in a way that has the dilogarithm of the argument squared, negative the argument squared. Interesting, with the 36 there. So there's a natural 36 structure in the system. Really nice for us because we found the natural structure to look like an 8/36. There's also another interesting set of summations. So these are 2 infinite sums. And we're going to go over these on the board a little bit because they look a little daunting. It's a big equation. It's harder than some of the other equations to talk about the Giesking manifold, right? It's got a lot of pieces, really, when you think about what's going on. But it turns out the pieces aren't really that complicated to interpret. So we can actually parse this, and we will. Let's expose ourselves first to all these other features that we talked about in our structure so far, the domino tiling constant. So here's the notion of domino tiling, different ways you can tile a grid with dominoes, okay? And note there, the Fibonacci number, f of n plus 1, so the next Fibonacci number has an equation that defines how you get to the next Fibonacci number. But it gives a number of ways. That equation is the same thing as the way you calculate the number of ways for 2x1 dominoes to cover a 2x(n) checkerboard. Okay, so the Fibonacci number itself is connected to the logic of how you could fit things together with the Fibonacci structure.
Like playing dominoes.
Yeah, another thing to really notice here, there's a mod 32 structure in the system. Mod 32, that's one of our divisions of the system we're talking about. So that's really nice. It's really nice, of course. It has to be compatible. And the domino tiling constant is equal to Catalan constant over pi. Catalan constant over pi. Both very central numbers in geometry and our system. So that's how central it is to the structure. And now we can look. These are all then components, structural components of how the system is being fit together. There is a domino tiling story that's part of the system. That's a nice clue. All right, let's look. That was domino tiling. Dimmer constant. It's not so easy to come to, so I recommend going to Wolfram Alpha, typing in Dimmer constant, and you'll see right away it's got an exact form for it. E, 2 times Catalan constant divided by pi, all in the power there. Okay, really beautiful. Also, I want you to check. Let's click on the number here, and then come on down. Oh, look, there's actually a symbol specifically for this arrangement. So the Dimmer constant d sub d is this, and you can follow the trail further from there. All right. Let's go to, what are we on this one? Oh, more on Catalan's constant and Catalan's constant. Cool. So this is the quick thing to introduce. We'll do it up on the board. But Catalan's constant is equal to this sum from k equals 0 to infinity of -1 to the k, which just means we have alternating sums. So the signs are -1, +1, -1, +1, of 2k plus 1 squared. how do you think of 2k plus 1? What does that represent? 2k forces you to be an even number. Plus 1 forces you to be odd. And since k can be any number, because that's the thing we allow to run through the sequence, k changes in number as we go up, that always odd plus, or always even plus 1 means always odd. And you count through all the odds. If you start through 0, if you start with 0, well, we'll do it on the board, it'd be easier, but 2 times 0, 0 plus 1, now just 1 on the bottom. Okay, so we start with 1 and we go all the way up. But this sequence is a beautiful, symmetric, simple to describe sequence that weaves together to form the Catalan constant. Last one here. Great. It focuses on different details, and I really like this. This structure we just talked about builds this continued fraction. Or sorry, this continued sequence, right? It builds 1 over 1 squared minus 1 over 3 squared plus 1 over 5 squared, all the odds, every other sign as we go. Okay, it also has a continued fraction that I think it'll have down here. Look at this connection. This is G is Catalan's constant. Notice how we switched to G. I don't know exactly why, but here it's now on a G. Oh, are we on Wikipedia? Is that what? Yeah, no. We're on Wikipedia. So here in Wikipedia, the Catalan's constant is instead of C, it's now a G. And I use a K, just to confuse you further. Okay, a lot of other beautiful, simple integral connections. Look at the gamma function structure that gives us the Catalan constant. Okay. Elliptical integrals, both kinds, connected to the Catalan constant. Okay, this is very beautiful, fundamental, structural things that really need to be understood to understand the structure, the dialogarithmic bipart form of the hyperbolic figure 8 knot puts into existence for us. Okay, so here's one way to try to look into it. Here's the continued fraction, right? If you use the Euclidean algorithm for finding the lowest common divisor of any system, so if a system is made out of parts and you want to find what's the smallest piece, the smallest Lego block in the structure, then you keep using this system until it bottoms out, until there's no remainder. Okay, now you could use a system and it never bottoms out. It's an irrational number that you're talking about, and so it just goes on forever, giving you more and more and more numbers with no zero for a remainder ever. But this structure has a very easy to state, in fact you can kind of see it, other than the first one, we then go in powers 1, 3, 5, 7, 9, so all the odd numbers here are increasing, but always to the power of 4. And that's the structure that continues. And over here, 1 plus 8, so after the first one we have 8, which is 8 times 1, 16 is 8 times 2, 24 is 8 times 3, 32 is 8 times 4, and we just keep going. So the multiples of 8 go up by 1, count 1 multiple of 8 each time as we go down, and the power is always 4, but we're just tracking the odds. So this division structure gives us the Catalan constant. Here's another way to do it, right? If you're just leaving all ones in the numerator and trying to write them down, not nearly as beautiful to me. There are other forms for the same one. All right, back to the board we go. Let's remember that 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9 minus ... is equal to, do you remember? Do you remember? All the odds in the bottom, every other sign's different. Close. Closer. All right, another one, a very famous one. If you try to think of, well, this is a pretty simple sequence. If you need to put together an infinite sequence, but you want ones that are simple to describe, right? Very short code and have it just iteratively go over and over and over. But you want to be super simple from the beginning. How do you make it simpler than that? Maybe make them all pluses or all minuses, but then either way it's going to blow up, right? So it doesn't converge, so it's a little less interesting in some way. But you might look at how it goes to the blow up to the speed and so on. Maybe you might say, well, instead of just taking the odds, why don't you just take all the numbers? Seems maybe in some way simpler. Let's say 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. That's a bad 4. Plus 1 over 5, and so on. This one is now the natural log of 2. What I really want, if this is the first time you've seen this, I mean, it probably isn't because it's a very famous equation here, but what I want you to see is when we're talking about piecing things together by dividing up into the number of pieces, this is all divisions here. But there's a whole set of possible divisions put together in one-to-one opposite form. We get log of 2. This is a very geometric number. 1 over 1 minus x. This is the geometric sequence. Okay, very simple. 1 over 1 minus x. It's equal to x to the 0 plus x to the 1, plus x to 2, plus x to the 3, and on and on. 1 over 1 minus x is equal to the sum of all the powers of x. Okay? And this is the most important and central of all the sequences, and we call it the geometric sequence. Now there's another one called the alternating geometric sequence, and it's the next most important, or maybe the same most with it, because it's the same story. Alternating geometric sequence. This one is 1 over 1 plus x. And now it's no longer equal to this sum of all the powers. Now, oh yeah, because of the name, of course, I gave it away, huh? Is we just changed the sign of every other one. Okay, what's the connection between these geometric numbers and these fundamentally simple sequences? Right? Well, if you have 1 over 1 plus x, if you have that structure to begin with, this alternating geometric sequence structure, and you want to ask, what's the most creative thing that could be equal to? You can set it equal to any number you want, but if you don't set it equal to a number, if you're not wanting to pick a creative fixed point, you want to pick a creative algebraic point, it's the one where it feeds into itself, which means equals x. You see what happened there? The moment I made this equal to x, all of a sudden now, the whole thing is x, right? X is equal to that. So whenever I have this x here, I can replace it with, let's rewrite, 1 over 1 plus the whole thing, which is 1 over 1 plus x. Oh, but x is equal to that thing again, so let's just go all the way down. The whole tower comes in when we just set this structure here, the one that defines the alternating geometric sequence to begin with, equal to itself. It iteratively copies and then scales down. So this hopefully maybe gives you the feeling of a fractal, right? This is a fractal. This is something that's divided up into another piece and put together smaller and smaller and smaller and smaller pieces. But this is the symmetric fractal because all the pieces are equal. Okay, you don't need to be symmetric to use this structure. Another thing though is what happens if you take the derivative of this? Oops. One over 1 plus x dx is equal to log of
x plus 1.
x plus 1. Okay. What do you see? We integrate this structure, we get the logarithmic structure. Offset by an argument of 1, but still the whole logarithmic structure is built in there, right? If we integrate the alternating geometric sequence, we're immediately at the natural log. The natural log that has this kind of geometric structure in it. Yeah, in fact, look, if you pick 1 for your x, then now this is natural log of 2. It's fundamentally beautiful, but the point is the logarithmic structure that we're really in love with in math, right? The whole structure itself comes in from the picture. I mean, maybe it's obvious because we started with a dilogarithmic structure to begin with. So yes, it's all a logarithmic balance. But it's easier to understand, I hope now, to see how this alternating series is the structure in the system. So we have a system that's breaking into pieces, and the pieces have to be glued together, or the edges have to fit next to each other, even though you're dividing a number of pieces. So all the number of times you break into a number of pieces have to be matched to number of times that you seamed together. We had the sequence before on the screen. The sum from n equals 0 to infinity of -1 to the n over 2 times n plus 1 all squared. And that equals the Catalan constant. Whenever you see a structure like that, you might want to ask yourself, what happens if we change something? Maybe we could change that +1 to a -1, or maybe we could say this one's a plus sign, so the alternating part goes away. Let's do that. So n equals 0 to infinity, and now we're just having a 1 up top, 2n plus 1 squared. What do we equal now? Now it's 2 pi squared over 32. Okay, so this is a structural component that we should care about, matched to the same system. So if you see a 2 pi squared over 32, you would think, oh yeah, this is a twin to the Catalan constant. A twin in the sense that this one alternates and this one doesn't. It's the thing it differs on. Other than that, structurally they're the same. Great, and not only are they structurally the same, but it's a structure that we can easily intuit. There's a way of writing the Giesecke constant in terms of summations.
Yep.
Yeah. So first I'll break it up like this. Square root of 3 over 2. That's one piece. Another one is, I'll explain why I'm breaking it up like this. Square root of 18 over 8. But then we have this 3-part structure here. 1 plus the sum from n equals 1 to infinity of 1 over 3n plus 1 squared minus the sum from n equals 0 to infinity. That was 1, this one's 0, of 1 over 3 times n plus 2 squared. Close brackets. Now there's a lot there, but if we go piece by piece, it's going to seem a lot less daunting. We just need to learn how to interpret these in words when we look at them. So first piece here, square root of 3 over 2 is something that we already have very familiar geometric comfort with. What's a way we can geometrically interpret what square root of 3 over 2 is?
Think of a cube. You have a cube. You go from the diagonals.
You can get a square root of 3.
Root 3.
Yeah, and then go halfway, you're over 2. Good. There's another one. If you take the simplest triangle whose sides are all 1, then the long side, meaning if you go from any point to the middle of any other opposite side, say the top one straight down to the bottom, or this one to there, all of them, the other opposite length in there is square root of 3 over 2. By the way, that was also shown to be the minimal possible edge length for a Mobius strip.
I think it's the width is root 3.
Root 3. So it's times by 2. That makes perfect sense, because if we extend this minimal triangle, then we can glue our edges oppositely and oppositely.
That's what we actually made when we.
Yeah, exactly. And then we get the minimal possible Mobius strip. Great. Let's talk about 18 over 8. Well, we're associating 18 to be the degrees of freedom available to the Planck charge, and the 8 is the degrees of freedom available to the modular structure of the Planck mass. Great. So I'm just going to leave it at that for now, and that's what we're thinking they are. So it's a ratio of how we're using those degrees of freedom. Great. But what are we doing structurally? When we're breaking up piece by piece and putting them all together, we could be alternating. There's a sign change here, so you can be subtracting some of the pieces as you do it. Fine. But what kind of pieces are we talking about? So this is the piece now, everything in the brackets that I want to talk about. In fact, I think the one's simple enough. Let's just talk about this one and that one. First of all, the 3n plus 1 in the denominator. Numerator is super easy, 1 over. So we're talking about division structure, 3n plus 1. But what is 3n? What does that force on you if we have a 3n? It's tripled. Okay, so it's a tripled structure. But then plus 1. And the next one over here, we get 3n plus 2. How are we supposed to interpret that? Well, if there was a third one with 3n plus 3, right, then after that it repeats. Because there's the structurally 3n, you've already multiplied by 3. So that multiple restricts you to how many offsets are valid before you start recycling the offset. Okay, so here we're taking 2 of the offsets from our triple division structure. Why does it have triple division? We don't know. We're just noting that it does at this point. It has a triple division structure, but only uses 2 of the offsets in that triple division structure. It's weird. Wait, don't we remember in our pattern? It was every third one was a 0. Oh! So we can just plus 0 here and say we're doing all the pieces in the 3-part structure. Okay, let's think of it that way. We got plus 0 at the end, all the pieces, just one of them zeros all the way out. All right, now it's a lot more sense. We got all 3 pieces of a triple structure, also then squared. We got to keep that in mind. Okay, so whatever it means to be dividing by 3, all multiples of 3, and the third one always zeroes out. So every multiple of 3 in our structure goes to 0, so we didn't have to write it down. But to put all those pieces together, and then we get the Giesecke manifold. So there's a 3 that's inherent to the structure here. That's a very important thing. Okay, so I'm going to leave it at that for now. This is just an investigation, look further into some of the structural components that are induced in the world if we make the stage of the hyperbolic figure 8 knot. I hope you guys really enjoy exploring the story we're piecing together. Remember, we're back tracing the story. We're starting from the data points and putting together a story that gets revealed from the pattern in the data points. And now, the entire pattern seems to emerge from a simple story of you have the basic, simplest possible structure that you can build, built by the hyperbolic manifold that can fold back on itself, inside of itself, and so on, called the Giesecke manifold. The simplest possible one that can do that. And once we root that structure into the world, all the possible decomposition pieces of that simple structure, remember it has 5 bases, so 5 unique kinds of boundaries on completely different scales from each other. But it has 5 bases, 5 boundaries called the Planck constants, and those now are revealed as geometric structural components, the literal division boundaries of the simplest projection, or the external projection, complement of the simplest internal hyperbolic figure 8 knot, or hyperbolic structure that can be built. So all the partial decomposition parts of that match, or when we take all those decomposition parts and compare them against the measured values for the constants in nature, we get a really powerful pattern emerging, showing us what kind of structural components are actually holding together all of these boundaries. So we now have a way to peer into the structure, right? And that's when we find one system that shows all of this actual division structures, all the transforms and actions and things that you can do, but they happen to match perfectly to the scales and dimensions of the transforms in physics, the constants of nature in physics, the things that determine how things occur in reality. Then we're unpeeling a geometric story, one that we can understand on a much richer level than we've understood before. One that gives us detail to the structure of essence itself, of things that will persist, of things that could be noticed or observed or measured. Okay? The structure of measurement is a good way to think of it. It's what's available to the structure of measurement. Well, in order to be available to be something that you could measure and that you could also measure, right? We can both go check it. It must be able to persist. It's its first feature, because if I go measure it and then it goes away, it doesn't exist anymore, and you try to measure it and it's not there, we're never going to agree on measurements. So if we want to talk about a persistent property, if we want to talk about a property that we can measure, it needs to be a persistent one. And then we realize, wait a second, all we're really interested when we're asking about what is the structure of reality, why does everything happen the way it happens, is we want to understand, why do the things that persist? Why is it those that are the things that are persisting? If you can understand a geometry that naturally persists, you are given a framework, a story that can make sense of all the degrees of freedom you're trying to make sense of in physics. The degrees of freedom that allow you to understand with visual access, with animations, with rich intuitive grip, what happens in chemistry. When you do a chemical reaction, what's physically going on? What's geometrically happening? When DNA is doing its thing, what's geometrically actually happening if we could zoom in? What's changing? What's transforming? Why is it still stable? Why are those the states that are still stable? The whole structure itself has to have a system of stability if you're going to ever answer those questions. And here, we're investigating the simplest known, the simplest possible hyperbolic structure, and noticing that it maps very, very beautifully to the division parameters or action parameters of physics. This is a beautiful thing to make a connection to, okay? This is a backbone that's actually available to make sense of the story you're after, right? If you want to understand the constants of nature, you have to understand why they're doing what they're doing. If you have a system that keeps itself going, but it must divide into pieces and slide along its own boundaries and make these different scales of actions, always keeping itself going, just to persist, well, all of those division actions, if they happen to define a system of persistence, they will then be the action parameters of that domain, right? They literally give you the ability to, at a glance, in one framework, hold in your head a system that holds all those parameters, right? It's much more than a whiteboard talking about 2 or 3 constants at a time. It's a picture that divides internally, structurally, exactly in the proportions of all the constants of nature. This is a fantastic story because it gives us the backbone for what it means to be an explanation for those features, right? It gives you both the frame of being something that persists. In order to be something that persists, you must be able to geometrically fold back on yourself. And to be a manifold, the simplest one available is this. Now, can you make more complicated ones? Yeah, we live in more complicated ones. But what we're really describing when we're talking about a system that's simplest to make is the simplest one that can divide. And that's the one that has all the constants of nature in it. Which means what? Well, if you have another system that's formed somewhere else, dividing, completely separate from that, they're going to both have the same constants of nature in it. But if they intersect, if they overlap at all, then the division structure of one matches the division structure of the other. So they have available degrees of freedom by which they can interlock. They can actually coexist with, but they always obey the same rules. So the rules of physics define the stage. They define the division parameters that hold everything together. They define the limiting speed, the limiting acceleration, the limiting jerk and snap and crackle and pop. They define the momentum limits, right? They define all the actual structural components that hold the system together. Now, you could imagine a different system, a more complicated system. But I think what we're noticing here is that all the available systems can only be combinatorial components, like put together of this simplest system. They are built together as Lego blocks from the simplest Lego blocks. So you can just make it combinatorially more of them to make a richer thing with many, many, many kinds of atoms in it instead of just one kind of atom, the helium atom. So this system, I think, we're describing as the simplest one. It's just one double cover of the Giesecke manifold, one figure-8 hyperbolic knot on the middle, on the inside, and the external N hypersphere of maximal projection dividing perpetually on the outside about that boundary on which the inside, the hyperbolic figure eight, now it's always inverting on itself, right? So it's keeping the outside projected under the same pressure all the time, and all of its boundaries are continuing to move along their balance. Once we have that, we've got a system that we can penetrate perceptually, that we can conceive what's going on. We can get the gears on the inside and peer into them. We can model it in a computer and zoom into that scale and see the division structure there, and zoom out and see how much it changes. It looks totally different on this scale because it's a fractal, right? It doesn't stay the same on every scale. It can be repeat. It can look similar again as you get up on higher scale and over, but it doesn't stay exactly the same. So I think what we're discovering is that the rules built into math, the rules for how we divide things up to find the lowest common piece that holds things commonly together under logic, are the rules of the simplest manifold, the simplest stage. And the rules of physics are simply the division parameters of that simplest stage. But the thing is each of those complexities perfectly match to one of the features we've measured into the world. That's the beauty of it. It's 288 actual forms fit together to balance against the internal knot of the hyperbolic figure eight knot, making a total sum of 0, by the way, right? 1 and -1, sum to 0 in the projection. It's very exciting to be at a stage where we have at least a framework of the kind of story that could make sense of what we're after. It's a framework that partitions itself, that keeps itself going, that is perpetual, whose division parameters happen to be matching up exactly with the parameters that, once you assume the Planck constants fit together to make the constants of nature. We're trying to get to the stage where we have animations, because interactable animations where you could zoom in and see something structure, at will, and kind of develop an intuition for what the structure is, will make it so that we can see how all these structural components literally give rise to our favorite components of reality. And when we can see how the gears fit together, it's automatic that we can find the ways to make them do work for us on purpose. Yeah, it's only our blindness of the inner workings of quantum mechanics that keeps us from using the outputs of quantum mechanics, right? Right now we can statistically use what it does. It's a completely different game when you deterministically use its outputs. Completely different game. The waste of energy is on a completely different scale here. And in this case, it's not waste of energy, it's accessing the energy. So yeah, it's flipping the script in many different ways. But the exciting part here, I hope, if you're tuning in, is that we're finding a story for structure itself that naturally seems to map perfectly to the constants of nature. So that's it for now. Next time, hyperbolic surfaces of revolution. We'll talk about a few different kinds, talk about their properties, and then hopefully, if you're poring over the details of the constants of nature poster that we found, many of those properties will stand out right away. So hopefully we can develop together our intuition of all these hyperbolic boundaries, of all these ways of chunking things up hyperbolically, right? If you're going to break up into pieces, you need to use boundaries to do it, and we need to use the hyperbolic boundaries in a hyperbolic system. So we need to get to know all the different kinds, the individual slices of this hyperbolic structure. That's what we need to really get focused on. So next time, hyperbolic surfaces of revolution, we'll do a few of them, and until then.